Hello, everyone, and welcome to today's webinar on how to connect circuits. My name is Devon Pianosi, and I'm an applications technician here at Voltera. Today, we will be talking about some of the different connector technologies and strategies you can integrate into your projects. First up on the agenda, we'll begin with the design, strategies, and techniques we have used here at Voltera. And we'll also be showing a few example projects showing how connectors are integrated into flexible hybrid electronics. We'll discuss some of the common failure points, challenges, and design considerations in integrating connectors into flexible, stretchable, or flexible hybrid electronics. After that, we'll discuss different strategies and considerations for the selection of materials and components when designing for flexible or stretchable applications. Once we've finished reviewing the various methods we've used for making connections, we'll take a quick look at a project we recently completed to showcase these methods. We're lucky enough to be joined by Simon Wong, a project engineer at Panasonic, who will then cover connector classifications, attachment methods, and Panasonic's product offerings in this space. After Simon is done, we'll spend the last 15 minutes or so with an open Q&A. So if you have any questions you would like answered, please submit your questions using the Q&A feature that's located on the Zoom toolbar. We also have a team in chat who can provide answers during the session. Finally, be sure to stay to the end to receive a promo code worth $2,000 off the cost of a Nova. We also will be announcing a special ink promotion here at Voltera. So, when we design flexible hybrid electronics, connectors are often the first mechanical link to fail. So it's critical to keep their strengths and weaknesses in mind. Unlike traces and other printed elements, connectors introduce a rigid element into an otherwise flexible system. This mismatch means that bending, twisting, or other stretching can introduce localized stress at connector locations. For example, some common failure points that we've encountered at Voltera are substrate failure, where TPU failed over time due to increased strain next to a connector. Conductive ink failure, where silver conductive ink has cracked due to repeated strain near rigid connector bodies. Incompatible materials, where incompatible materials fail to adhere to the substrate, causing total material failure. Component delamination, where the lack of encapsulation or mechanical isolation causes components to be popped off of the circuit. Generally speaking, there are three major challenges that dominate connector integration into flexible hybrid electronics. Number one, mechanical stress, so strain at the solder joint, crimp location, or adhesive bond. Substrate compatibility, ensuring that the connectors and conductive inks actually bond and remain stable. Long-term reliability, performance under repeated bending cycles, thermal changes, or environmental exposure. For example, in a medical sensor, body motion generates multi-directional stresses. Without a stiffener, these forces concentrate directly on the connector and can cause premature failure. A stiffener acts as a kind of mechanical buffer, distributing strain away from the joints while allowing the rest of the device to remain flexible. In contrast, with a flexible sensor strip that is meant to be connected and disconnected repeatedly, the challenge might be less about movement-related strain and more about insertion cycle durability and connector wear. Successful connector integration depends on how well the substrate, conductive ink, adhesives, and encapsulants all work together. Factors like the coefficient of thermal expansion, adhesion chemistry, and fatigue resistance must be carefully matched to prevent issues like cracking, delamination, or creep under load. Environmental resistance also matters. Factors such as humidity, sweat, and UV exposure can degrade adhesion or corrode contact surfaces over time. The substrate choice is also critical. PET and polyamide have very different thermal expansion properties, which can influence how well a connector adheres during soldering. Stretchable polymers like TPU or Baolex also add further complications because they are elastic, which makes reliable mechanical fastening even harder. An example of this we've experienced was during one of our encapsulation tests. A resin completely failed to bond with the TPU substrate, even though it performed well on a different polymer. And this just shows why material screening and testing are essential. When selecting connectors, try to prioritize smaller, low-profile designs that have features like strain relief and that minimize leverage forces at the joint. Make sure the connector's pitch, pad size, and termination methods, such as soldering, anisotrophic conductive film, or adhesive bonding, are all compatible with your chosen substrate and ink systems. Also consider the intended use case. For example, a ZIF connector might be ideal if the connection and if the circuit is designed to be connected and disconnected often, while a crimp connector might be more reliable for permanent attachment uses. Try and keep connectors aligned with the neutral bend axis whenever possible to reduce tensile and compressive strain during bending. Follow bend radius guidelines, which is typically 5 to 10 times the substrate thickness, depending on the material, of course. And use stiffeners or encapsulants to reinforce attachment areas. If able, try and route traces away from high strain regions, and this will improve long-term durability. Placement strategy can also make or break a device. The general rule is to put connectors in low strain zones. These zones are typically near the edges or corners of a circuit where mechanical displacement is minimal. Reinforcement is just as important. Simple methods such as adhesive backers, stiffeners, or encapsulant can greatly improve fatigue resistance. In contrast, placing connectors across a bend that adds stress, almost always leading to a problem like traces cracking and substrate delamination. In our gold echocardiogram electrode project, we printed gold traces on a TPU and integrated a snap connector. To reduce strain on the connector, we laminated a PET insert beneath the connecting area. This prevented the TPU from overstretching the gold ink, which that could become brittle under elongation. So as a result, the design maintained reliable signal performance even after repeated flexing. One other point worth highlighting is the balance between cost and reliability. In early prototyping, it's tempting to choose the cheapest connector that fits the footprint, as the primary goal is just to usually test whether the circuit works at all. However, choosing a connector of questionable quality can lead to misleading results caused by poor electrical contact. Once you move forward with functional testing or field deployment, that choice can come back to haunt you. Lower cost connectors often use thinner plating, less robust housing material, or fewer reinforcement options. This can lead to problems like poor contact retention, rapid wear, or even corrosion in humid environments. For example, in the Gold ECG project, we utilized some low-quality snap connectors, which resulted in issues with signal fidelity and connector reliability. We initially thought our design had a problem, but it turned out just to be the snap connector. When we switched to better snaps, the issue resolved itself, and we were able to progress and finish with testing and finish the project. Recently, we built a demonstration project where we designed and printed a connector breakout board using V1, then connected it to several different flexible sensors, which were printed on Nova with different functional inks. The purpose of this project was to show how multiple connection strategies can coexist in one system depending on the substrate and application requirements. In the project, we demonstrated several connectors and sensors, such as a carbon strain gauge, which was connected with a printed polyamide ribbon cable using anisotrophic film. So a Z-axis tape or anisotrophic film conducts electricity in a single direction, in this case between the printed ribbon cable, the strain gauge, and the rest of the circuit. This was showcasing a reliable stretch to flex electrical connection, often used in products like LCD displays. We also printed a carbon ribbon cable, or a stretchable ribbon cable rather, on TPU. It was reinforced at the ends with stiffeners to provide additional mechanical strength. The connector we chose were insulation displacement connectors, or IDCs. We attached the connector by penetrating the silver conductive traces and the stiffeners, and this maintained a reliable connection even when stretching the TPU. We also printed a capacitive touch sensor, integrating. We used a zero insertion force connector, or a ZIF connector, for easy testing and replacement cycles. This solderable surface-mounted ZIF connector was used to showcase a method for reliably and repeatedly connecting and removing a sensor. We printed a flex sensor with a carbon and silver ink. It was terminated with a crimp connector to highlight a robust, low-cost connection method. This crimp connector demonstrated a reliable physical connection that didn't require special tools or materials to form a robust electrical and mechanical bond. These are some of there are others connections methods used in this project as well. And if you would like to know more, you can check out our website and our YouTube channel. Each application requires unique consideration when it comes to selection of materials, substrates, and connectors. There's no one-size-fit-all solution or magic silver bullet, despite using silver ink. So that concludes the Voltera portion of our presentation. I'm now going to hand off the reins to Simon Wong, who, as I said, is a project engineer from Panasonic. So, take it away, Simon.
All right, thank you. Hey, buddy. My name is Simon Wong. As you mentioned earlier, I'm a product engineer at Panasonic. So today I'll just be going over a little bit about our connectors and some general information and best practices. So bear with me while I get this up. All right. So first off, we're just going to be going over a little bit of an overview of connectors. So starting with different types. So when it comes to connectors, there's generally four main popular types when it comes to board-to-board connections. So we have our card edge, flat cable, our two-piece stacking connectors, and FPC connectors. On this table, you can kind of see like the pros and cons for each type, as well as popular applications for each. So card edge types are single-piece connectors that connect boards by the edge into the connector. These are generally low cost, they have high pin density, and they're widely used in modular electronics. Cons, however, is that these can be a bit more difficult to mount due to tolerances, board warping, and mechanical wear. Some popular applications for these would be things like PC motherboards, PCIe slots, memory modules, and also industrial backplanes. Next, talk about a little bit about flat cable connectors. So flat cable connectors are connectors that use thin cables that are tied together in a strip and crimped. The benefits of using these is that these are generally flexible and easily terminated since you don't need to strip the wires. The drawbacks, however, is in its lower signal integrity since it's a bit more vulnerable to noise and it can be a bit bulkier. These are mainly used in things like legacy PCs, industrial controls, and also low-speed data buses. Next, we have the two-piece stacking connectors or nail pitch connectors, and these are a two-piece solution with a socket and header. These are very compact and don't require cabling, though they can be mounted in a board to FPC configuration. Main drawbacks for these is that they can be a bit more expensive and alignment during assembly is very important. Applications for these are generally used in more smaller types of devices, so things like smartphones, IoT modules, wearables, and mobile electronics. Lastly, we'll talk about FPC connectors. So these are single-piece solutions where FPC is locked in with the lever. These are more compact. These are compact and flexible, but they can be a bit more delicate and have limited cycles. And these are very commonly used in displays and also things like smartphones and laptops. So for the purpose of this presentation, we're going to be focusing mostly on narrow pitch and FPC connectors, since that's what Panasonic specializes in. And again, here you just see a comparison between the two, and you can see how these can be mated on the bottom. So in particular, narrow pitch connectors can be mated in a board-to-board or board-to-FPC configuration, and FPC connectors just have a single-piece solution where you just have the FPC locked in with a lever. So here we just have a comparison between the advantages and disadvantages for both types when it comes to different types of features. So in general, for nail pitch connectors, these save a bit more space. They have higher design freedom and ease of mating, while FPC connectors are lower profile. And the next couple of slides go a little bit more in depth into the advantages of each. So narrow pitch connectors are arranged in two rows, which allows them to save more space and doesn't need additional space for FPC insertion. Because of the dual rows, you can fit double the amount of pins in around the same space. There's actually some connectors on the market with quad rows, which save even more space, but those have their own trade-offs as well, mostly involving mechanical strength. In terms of mated heights, narrow pitch connectors generally will require more vertical space. So for things like the subboard as well as reinforcement plates, whereas FPC connector does not. And this is one of the advantages that the FPC connectors have over narrow pitch since it's unnecessary to account for that additional height. When it comes to design freedom, narrow pitch connectors generally have more freedom when it comes to design, since these can be vertically inserted, they can be in the center or the edge of the boards, while FPC connectors generally need to be on the edge, since the FPC has to be inserted horizontally. In terms of ease of mating, narrow pitch connectors have the advantage here, since these can be mated in a single step by just simply pushing it in. And this makes it during assembly, since this only requires that single step. FPC connectors need an FPC to be aligned, inserted, and then you need to manually close the lever. So when it comes to narrow pitch connectors, generally there's a snap or tactile feedback that also makes it easier to confirm that it's been mated. So it's some of our customers prefer the narrow pitch connectors. It's because of that kind of feedback you get as you when it's mated, so you don't need to really confirm as you would with other types of connectors. All right, next section, we're just going to be talking about best practices and some general guidance when you're using narrow pitch and FPC connectors. So first off, disconnection prevention. So when it comes to disconnection prevention, we generally recommend using a cushioning material and reinforcing plate for narrow pitch board to FPC types to hold it in place and also prevent displacement. Recommended holding force. This material should be higher than the insertion force, but not too much higher to prevent damage to the connector. And the force should be centered over the center of the connector. When it comes to board-to-board connections, it's best practice to fix the boards in place so that the PCB doesn't move and cause damage to the connector. So generally, some type of spacer could be used or screws to hold it in place. When it comes to soldering onto boards, the general recommended for method for these types of connectors, like narrow pitch and small FPC connectors, is to reflow. So depending on the connectors you use, it will have a different reflow profile. And on the bottom here, you can just see an example of a recommended solder profile for one of our connectors. And there's generally 4 stages for these with a rising temp stage, preheating, heating, and cooling phase. If next, we'll talk a little bit about manual soldering. So if it's necessary to manually solder, we recommend using something like a retractable knife shape type soldering iron and a thin wire solder. Well, that's around 0.3 to 0.4 millimeters in size for a connector of a pitch of 0.35 millimeters. Some other tips, it's important not to touch the connector itself or the contacts of the iron, and only touch the foot pattern to not damage the connector. So generally, you'll be using a metal mask to apply solder paste to your PCB for these types of connectors. And depending on the connectors you use, it will require different design or lamp patterns. So best to check with your data sheet for the relevant series. General process will just involve aligning the openings with the pattern of the board and squeegeeing the solder onto the board. So when you're also using these types of connectors for board to FPC connections, we usually recommend using something like a reinforcing plate to prevent solder peeling and PCB warpage. And just some general recommendations, something like a glass reinforced epoxy resin sheet. And the design of the plate should extend around 0.5 to 1 millimeter longer than the land pattern. And lastly, for some general mating instructions, mating sounds like a pretty simple step, but this actually turned out to be a problem during some assembly processes since these types of connectors are very small. So we've actually had several instances in the past where connectors were coming back damaged because the technicians were not mating the connectors properly. So in general, you want to roughly position the connectors, move slightly in the X and Y direction to check the position. And then when you kind of feel it find a place, you'll lightly press at the center, and then you should hear a snapping noise or some type of feedback when it mates. And lastly, you just want to check the height clearance to make sure that it's been mated properly. All right, next we'll be talking a little bit about Panasonic connectors and our offering. So with Panasonic connector, we have two main factories. So we have one in Japan and one in Thailand. Japan's kind of like the mother factory where all the connectors are produced, but we also have one over in Thailand for some series that require additional manufacturing lines. And here we just have an overview of our portfolio. So as I mentioned earlier, we mainly specialize in narrow pitch connectors as well as FPC connectors. Our connectors generally range from around 0.35 millimeters to 0.5 millimeters in pitch. So these are very small. And we also have some more high current types. We also have some automotive type connectors. These are a bit more specialty, something like a shielded connector, and also an optical connector. So when it comes to Panasonic connectors, we have four main factors that make up what we call our tough contact technology that makes them very reliable. So next slides go a bit more in depth into these, but as a high level, these are all made with a double contact or V-notch in between the contacts. There's a nickel barrier on the contacts. These are all made with a beveled contact construction. And lastly, we treat all the contacts with a porosity treatment. So first off, with this V-notch contact construction, so this is actually a patented technology by Panasonic. There's a V-notch in between all of our contacts, which gives it 2 points of contact, essentially seals it off so things like flux, dust, and dirt can't get in between them to interrupt continuity. Next, the bell contact construction. So the way our contacts are made is that these are actually bended into shape rather than being stamped out like some other types of products. And what this does essentially gives it more of a spring-like performance, gives it a higher retention force. Also, it makes it more flexible, so it's able to absorb things like shock and vibration better. There's also a nickel barrier on all of our contacts, so this prevents solder rise after reflow, and we were one of the first companies to adopt this type of technology. And lastly, a porosity treatment. So with gold plating, sometimes pinholes can form in the plating, which can be a cause for corrosion. And to combat this, we treat all of our contacts with this porosity treatment film. Essentially seals off these pinholes and gives it the same performance as a thicker layer of gold. And next, we also offer some power connectors. So these connectors can handle higher currents. And we have two main ways of doing these. Some of our series has power terminals on the ends that can handle higher currents. And some other series, you have the freedom to choose which pins you want to use for higher currents, although there is an overall current derating. And I'm not going to get too deep into like any specific series here for the sake of time, but just some interesting things. So this is our R35K connector. And you can see the pictures like it's about the size of a sesame seed. So really good if you need space savings on your board. So these can handle 3 amps current each on its power pins. And it also has a little metal flange that makes it a bit more robust. And these are just some examples of what I mentioned earlier as a type of power connectors that you have the freedom to choose which pins you want to use for current. So in this case of something like these, you can run up to like 1.5 amps per pin. And in the case, if you need high speeds, here we just have some different standards that these connectors pass. So most of our series pass up to USB 3.1, so 10 gigabits of speed. And next, we'll be talking about our FPC connectors. So our FPC connectors have both top and bottom contacts, so you don't need to choose a top or bottom type FPC. There's also holding contacts on one of the series, which increase retention force and also holds the FPC into place, which makes it useful during assemblies. Basically aligns it and holds it so you can lock in the lever without issue. And lastly, these are all made of a backlock structure. So these are delivered in the open position as opposed to a front lock type of FPC connector. And this saves a lot of time during assembly since you don't need to go around opening up all the levers as you would with a front lock. And lastly, since it's a backlock type, it prevents a common failure mode that you would get with a front lock, where sometimes you tilt up the FPC and opens up the lever on a front lock. And just some comparison data, as you can see, our connectors have around double the holding force of a competitive type of product, and with the holding contacts, it can be nearly triple. And a little bit about automotive connectors. So these are our CF1 and CF2 type automotive connectors, mainly used for things like BMS systems in cars. And the main feature of these is that these are surface mount and can be reflowed and has metal to metal clip contacts, which makes it very durable. And just some examples, we've been seeing an increase of using FPCs in automotive devices rather than the old way of doing things like a wire harness for these types of applications. And just some examples of how we compare to competitive types of products. And main selling point here is, again, that those metal and double contacts and the fact that it can undergo reflow. So you wouldn't need a manual process as you would with other types where sometimes you need to reflow it, crimp it, bend the FPC, and insert it as well. And lastly, this is our active optical connector. So these are basically small PCB mounted optical transceivers that communicate over an optical fiber. So electrical differential signals go in through the receptacle, it gets converted into optical signals in the plug, and then gets sent over to the other side where it gets reconverted back into electrical signals. And these are generally really good for applications that require things like high-speed transmissions, as well as immunity to noise and electrical isolation. And for these types of connectors, the optical fiber has two cores, so it can communicate in either bidirectional or unidirectional. So it can reach up to 8 gigabits per second in both directions or 16 gigabits per second in one direction. All right, that is all I have. Any questions? And please feel free to add it in chat, and I'll hand it back to Devon.
All right. All right, Simon, thanks. That was great. So now we get to the question and answer period, and we have some questions in chat, and I'll kick one off here. Someone asks, do crimp connectors work with stretchable circuits as well? I would say, generally speaking, yes. Crimp connectors can work with stretchable circuits. You may have to add a stiffener or some form of rigid element directly at the crimp location to limit stretching to fatigue at that contact point. There's also probably get flexible conductive adhesives that might also aid with the crimp connection stability. Do you have anything to add to that, Simon?
No, I think you got it.
All right. We have a question for you, Simon. Does Panasonic have any magnetic connectors? And if so, what are the pros and cons and how should they be used?
Unfortunately, we don't really have any magnetics connectors, so I can't speak too much about those. Our portfolio mainly just consists of the standard board-to-board and FPC connectors.
All right.
But,
We have another question in chat here. What can be the theoretical and practical minimum pitch of ink traces for high density connectors? Is use of the mentioned 0.35 millimeters or 0.5 millimeter pitch connectors possible in a reliable process? I would say definitely. Kind of trace widths for printed ink is very ink dependent, so you have to kind of manage your particle size basically is a major considering factor. I think what we say at Voltera is our minimum supported trace width is 100, and when we're doing our printing as a service, we try and limit that to 150 just so things go smoothly. However, customers in the field and ourselves internally have gone below 100 millimeter trace space or trace width. So achieving something like 0.35 or zero point 0.5 is certainly possible. Another question here. What would be the best strategy to connect a JST connector after printing conductive inks? So JST connectors can be through-hole or surface-mounted, depending where you apply that ink to. If you are printing on a rigid board, you can often just use it normally, however you would with traditional copper. Um, yeah, the through-hole connectors might not work so well unless you incorporate the silver to be printed with plated holes. But the surface-mounted devices, if you're printing on flexible, you would just then want to add some sort of backing or a stiffening element there. You can also connect flex to rigid. So if you reinforce the flexible circuit, you can then just plug it in normally to a rigid mounted board. Um, so this is a question for you, Simon. Um, do you have any connectors for high voltage applications?
The main ones for these are be our closest would be our automotive types. So those have kind of like a dielectric strength of around, I believe, like 1100 or 1400 in that area. But those would be the best option.
All right. All right. Somebody asks, do you have experience with connecting cables directly to flexible boards? We do have some experience with this. Generally, you'd want to incorporate some sort of connector, uh, like just soldering a raw cable onto a flexible circuit might not lead to a good time. But if you incorporate some sort of connector, so the have two mating connectors, that can certainly help. Again, this always gets back to try and reinforce the area that those connectors are attached to. So trying to limit the actual flexing at the connector location. You can use encapsulants. There are rigid connectors that have reinforcing built into them, but it's certainly possible. All right. Let's see here. Uh, this is a question for you, Simon. What is the highest voltage FPC connectors that you carry?
So when it comes to our FPC connectors, we generally have we actually only currently have one main series called Wi-Fi B, but I'll need to look that up. I believe it's around in the 50 volts range, but I need to double check. And again, that the CF connector would be the best, like I guess similar type when it comes to higher voltage applications.
Yeah, that's really interesting. Somebody asks about any circuit development attempts on soft polymers like PDMS. Uh, we're certainly interested in using materials like PDMS here at Voltera. Panasonic has a flexible, stretchable substrate called Biolex, which is a soft polymer. It's kind of like we call it an upgraded TPU. It's real nice to print on. And you can connect it with various materials, and there are inks designed to work specifically for it. All right. Somebody asks, do you have any experience to connect surface mount SMAs on flexible materials? So connecting uh, various uh, surface mount devices onto flexible material is certainly possible, but again, it always comes back to try and reinforce those connection areas and limit flex in those areas. So if you had a stretchable or flexible substrate or connection, uh, you want to just limit those forces, limit those stresses to reduce any delamination. So somebody has a follow-up. Do you have any references you could link about stiffeners, other ways to reinforce stretchable circuits for the use of these connectors? If you have any other questions, we could reach out to our sales team at sales@volterra.io. And any questions that don't get answered by the end of this webinar, feel free to reach out. All right. What would be some common mistakes manufacturers see with beginner designs? Uh, some common mistakes might be failing to incorporate best practices, especially for things like connectors on flexible boards. Flexible technology is kind of new and emerging, so a lot of people might be more used to kind of traditional PCB design practices, and those don't always transfer one-to-one to flexible and stretchable electronics. Uh, like a rigid board wouldn't need necessarily a stiffener, for example, to keep components in place. Um, encapsulation might be more generally used to like surround components to keep them safe rather than reinforcing mechanical properties of connectors. And then there are also just mistakes like general design mistakes. Is it recommended to glue larger connectors on flexible substrates? If yes, is there a possibility to use cartridges for automatic placing of glue traces? Uh, so it's certainly possible to glue down larger components and connectors. Um, our Nova can dispense various different materials. It doesn't just do screen printable electronic inks. You can also load it with various adhesives or dielectrics or resins or other encapsulation components. We recently did a project with another company where we were dispensing um, I forget the type of adhesive, but some adhesive onto boards so they could speed up their automation. So you can kind of precision set up adhesion dispensing so it'll dispense automatically exactly where you want it to. All right, so we're rolling into the end of this now. I'll just give people a reminder. We're happy to announce that we're having a great sale on conductive inks here at Voltera. We're offering deals like buy one, get one free, buy four, save 60%, or buy six and save 65%. And this promotion will be running until December 5th. And that's a perfect time to stock up on inks and get printing. And for those of you who have stayed to the end, thank you. You can use promo code connectors to save $2,000 on a Nova. So thank you all for coming and have a great night. If we didn't get to your questions, we try and save them. And you can reach out to sales@voltera.io if you have any other questions. I'm sure you could contact Simon or somebody at Panasonic as well. Simon, do you want to give your email or contact?
Yeah, can I put in the chat? But it'll just be simon.wong. So just basically my name at us.panasonic.com. Thank you.
All right. Sounds good. Thanks everyone for coming. And thanks again, Simon. You were a great help.
Thank you for having me.
And this webinar will also be uploaded to our YouTube channel after. So if you missed the beginning or want to revisit it, it will be on our company's YouTube channel. All right. Thanks, everyone. Bye.
Thank you.